Hello there and welcome to Origen screencast number 4. In the last video I showed how to use the basics of the compiler, but today I'm going to show a more real world example and show how you would use the Origen compiler to create a C header file for a model. Okay, so let's say I've been given the task to supply a header file in this format here for the device that I own or the IP that I own. So in this case I'm going to focus on the A to D block from the previous videos and create a header file for that in this format. Okay, so the first thing I'm going to do is within my templates directory I'm going to create a subfolder called headers, and then within that directory I'll make a file called A to D .h, and again that's going to be .erb because it's going to contain embedded Ruby. So whenever you're creating a new template, the workflow would normally be that you create the actual file in its native language first, and then once you have it working there, you then go through the task of making it a template so that it can be rebuilt in future for different product derivatives. So the first thing I'm going to do is take my header file example, I'm going to copy it all, and I'm just going to simply paste that into my new template here. Okay, so the first edit I'm going to make initially is to rename the file. So this one was called s32r.h. So I'm just going to quickly do a find and replace for s32r274 and replace that with A to D. Okay. Then in terms of the header here, we can simply delete this as appropriate. It's going to be version 1 of the file. I won't spend too much time on this, but you get the idea. You obviously just edit this as appropriate. Then coming down here, I'll leave this stuff here. And if you have a look at the structure of the file, the first thing it does have here is for the ADC module, it's got a structure defined for each register within the ADC block. Now, this file has called the A to D ADC, whereas in my model I've called it A to D. So to avoid any further confusion, I'm just going to also replace ADC with A to D everywhere. Okay, and then the next thing I'm going to do is basically strip out everything that I don't need in the file and keep a few examples around of the things that I need to generate with my code. So I'm going to have to generate one of these for each register, so I'll keep this example here around and then I can get rid of the rest. Now, from looking at this file earlier on, I know that at the end of this section there's an A to D tag here, or another structure here rather, which defines all of the registers in the A to D. So I'm going to need that as well. So I'll get rid of all these registers. So that basically what I need to do is generate this structure for every register, and then I need to generate this one tag which defines all of the registers within the A to D. So I'll keep that around as well. Now the file is going to do some other modules, so I can delete most of that. I'm just going to search now for that A to D tag reference to find the next place it's used. That's down here. So we'll delete all of that. I'm then going to have to define these two things here. And then from here on again we'll just search for A to D. I've got another A to D section here which defines all the registers again, it looks like. One for each A to D instance. Okay, and then I believe that's it. So I'll go to the end of the file now and delete all of that. Okay, so this has got my my file now in a structure where it only really refers to one IP, like I'm going to do today, and it gives me an example of all the things that I need to generate. So the next step now is to go through each of these one by one and make them dynamic. Okay, so before editing the file and starting to add some dynamic generation to it, the first thing I'm going to do is just run it through the compiler just to make sure everything's working before we start. So it's going to be Origen compile, and it's going to be templates headers. So that's the first time I've run Origen in this workspace, so you can see I actually invoked bundler there to install everything. Then it ran the compiler. And we can see that it's telling us that this is a new file. So this time I'm going to make use of Origen's capability to save this off. So I'm going to go ahead and do that now by just running that command there. Now if we generate it again, Origen will give me feedback that nothing has changed since the last time that I generated it. And this is really useful for when you're creating new IP like this, as it allows you to really monitor what the effect is of the changes that you're making. And this works exactly the same for patterns and test program files and really any files that you're generating through Origen. Okay, so if we go back to our header file, first thing I'm going to tackle now is to create this, this structure here for each register. So the first thing that I want to do here is surround this in a loop to make it generate one of these for each register within my A to D block. So we'll say dot A to D, it's going to be A to D0, we'll reference here, dot regs, that's going to return a hash of registers, so just say for each one of them, that's going to pass in the name of the register and the register object, and then for each register we'll do this entire section here and then end that down here. Now it's just a matter of going through this and injecting the bits that we need to be dynamic. So first of all, this is the name of the register here, so we can simply say this is going to be the name. Now in our case the name here is going to return a Ruby symbol, and that's going to be lowercased. Now the convention in this file seems to be that register names and bit names are all uppercased. So to do that in Ruby, what we do is we convert that symbol to a string, and then we've got access to all the string methods, and we'll just say dot uppercase to uppercase that name. And then we have, it looks like a description here. So if we go to the console and have a quick look at the register, so origin I, so it's going to be dot A to D 0. So let's just look at the first one, SC1. Now this register we can look at the description, which is here. So if you remember from video 2 I think it was, this register has now been sourced from an IPExact file which contained all the register descriptions. So they're all in here in the Origen model, and I can pull them out. So it's .description, and that returns me basically an array of strings where each string would represent a line. So I'm just going to take the first one here, the first value in that array, and inject that into the file. So here we can just say, we can delete that, and then we can say reg.description, and if you remember that's going to return an array, and then we can just say .first to pull out the first item in that description array. Okay, so let's go and run that to see, make sure we're on the right track here. So if we compile that file, now we do get changes, so we can have a look at what we've changed so far. Okay, so this is our original file on the left here, and this is the current thing that we're generating on the right. So we can see that the one on the left only had one register, but we are now generating a lot of them in the new file, one for each register. And then at the top here we can see that we are following the intended structure pretty well here, so we can see that this was the original. And here we've got A to D SC1 union tag, and we've got a description there. So that looks pretty good. One thing that I do notice initially is that there's no space here between each of these registers, so that's something that we can go and correct quickly. In the meantime I will save this off because we have reviewed those changes and we're happy with them. So if we go back to our template here, what I want to do is basically put a space at the bottom here. That will inject a space between each register as this loops around. Okay, so the next thing now is to generate one of these entries here for each bit. So this is the bit name here, and this is the number of bits, and this should all add up to 32 in this case. And then I've also got the bit description over here. So we'll go to the console and have another look to show you the method that I'm going to be using here. So we can say, again, it would be A to D.sc1, and there's an API called named bits. So if we call register.named bits, that returns an array of arrays where each subarray contains the name of the bits and then an origin bit collection, which has properties like the size of it, the position of it, and so on. So this basically has all the information that we need to extract here to generate that header file. Oh, and also the if we look at, for example, one of the bits, like the conversion complete bit, that also has a description method. In this case, you can see we have got multiple lines here. So we're going to assume that the first one is the most descriptive, that gives the summary. So we'll just insert the first line of the complete description into the header file. So coming back to our file here, we want to now do a loop for each of these named bits in the register. You may be tempted initially to indent this here and say, reg dot named bits like that. You can see here that my editor's actually been smart enough to not highlight this as Ruby, and the reason for that is that basically if this % doesn't start in the very start of the line, then it won't be interpreted as Ruby. So we need to start that from there. You can though indent this to show that this is inside this loop here, just to make it a little bit easier to read. So reg.nameBits, and we'll do that for each one of these, and I think that's going to be we'll call it the bit name this time. And this is going to be the bits here, and then again we'll have to end that block down here. Okay, so we can pretty much just delete all these, only need one example. So this is the bit name here, so we'll just do exactly the same as we did for the register. So it's going to be bit name, again that's going to be a Ruby symbol, so we'll just convert that to a string and then we'll upcase it. And then, so we can get rid of that. And then this is the size of these bits, so we'll say bits.size, we'll go in there. Okay, and then finally we want the description to be over here, so we'll just delete that, we'll just copy this. And that's going to be bits.description.first. Okay, that should be it. I think while I'm here I noticed that I do have the register name down here again, so we'll just copy that from up here to inject that down there. Okay, and now let's go back to our console and see how we're doing. Okay, so we'll have a look at the diff from last time. Okay, so that looks pretty good. One of the things that I noticed is that this needs to pad out to a full 32 bits, but here I'm only defining 8 bits and there's no padding in it. So that's one thing I am going to have to resolve. So the original had things like this here where it was just padding out, missing bits like that. So it's basically just the number of bits without any name description. So we need to fix that. Another thing that I noticed is that in the original these were all nicely justified, all the descriptions here. But I can see that in my case the descriptions are going to be get in and out here. It'd be nice to clean that up and try and fix it. So we'll look at that as well. So that's two things we need to go and do. So again, we'll save that off. This is the kind of common workflow when you're doing something like this. Come back and inspect what you've done, review the changes, then save them, and then go and add something else. So one of the first things I need to do is deal with the padding. Now that's quite difficult to do. We may have to start injecting quite a bit of logic here to do that. Fortunately, because this is such a common thing, Origen provides an API to do this for us. So if we go back to our console and have a look, what I called last time was .named bits. We can see that's got all those named bits within the register, and that's what's appearing in a header file right now. This named bits method will take an option called include spacers. And when we do that, we can see that it adds this additional bit collection here at the start, which will have the correct size to space that out to the full register width. So back here we can just say basically named bits, include spacers, it's true, dot each do. Now that will return nil for this bit name, and unfortunately that's exactly what we need in this example here, so that's just going to inject nothing there, and then the size there. So we'll just go and quickly check that that seems to work. So look at our diff. So here we get our spacer in here. I think in most cases it's the kind of upper bits of the register. Probably, yeah, here's an example here of it doing it down here within the register itself. So that looks good. I'm still left with the problem that I need to justify these. Also, I see that we're getting an empty description here for this register, so it'd be nice to leave this missing bit here, so it'd be nice to clean that up. So again, we'll go and save this off. Back to our header file. Now we could get fancy to try and put some logic in line here to inhibit this description. Well, actually, what we'll do first is we'll fix the justification problem. So one way to do the kind of problem here is that I'm generating this as one string, this as another string, and then I'm padding this on to the end. What we really need to do is we need to consider this as one complete string here, and then justify it or pad it out. So what I'm going to do is I'm going to convert this to basically concatenate all of this together here, and then add some padding to it. Okay, so what I'm going to do is change this into a string. Now within Ruby you can say hash curly brace to interpolate a value into a string, like that. And then I'm going to have my colon, and then I want the bits.size again, and then I want my semicolon here, and then I'll end the string. Okay, so now we've kind of we've joined these together into one string. I didn't need to include this because this is a constant for every single bit, so that's not going to change. And then because it's a string here in Ruby, we can just say left justify, and then we'll pad it out to, let's say, I don't know, 30 characters. Let's go and review that. Okay, so here we go. So this looks nice and neat now. These are all nicely aligned. Last thing I need to do here in this section is just to get rid of that empty description there. So this is an easy one to fix. So what we'll say is we'll just say basically in here if bit name. So if the bit is a named bit and not a spacer, then we'll include that line there. Else we'll do something else. So we'll just copy that line down here, and we'll just delete the description. Nothing fancy really. So go and look at that and confirm that this section is now done. So we can see now we've cleaned up that empty comment. And basically now we've got a nice structure defined for each of the registers in our A to D block. Okay, so the next section we want to concentrate on now is to create this additional struct which has one line basically for each register within the A to D. This one should be reasonably easy to do. So back to our template. So as you might imagine, it's going to be a variation on what we just did. We basically want to do that register loop again, so we'll just copy what we did up there. We can just end it here. We can get rid of all these additional ones. So very similar to above, what we want to do here is basically just substitute this name and then put the description in. I know I'm going to have that same sort of justification problem as I had before, so I'm going to put this whole thing in a string here. So it's going to be A to D, and then that's going to be basically name, string.uppercase again, underscore tag, and then I've got the name again. Then we have a semicolon, then that's us done, and again we'll left justify that to 30 places again. Okay, like that. And then we'll just copy the description line from above here. Okay, that should be it. Let's go and check that that worked. So I forgot to save it the last time I was here, but the new bit's down here, and we can see that that looks pretty good. I've got one line for each register, and again it's nicely justified and seems to do what we want. Okay, so we'll save it this time. Now this next section looks pretty simple. We just want one of these for each A to D instance. So we can say dot A to Ds in this case, dot each do A to D instance. Now this dot A to Ds in this case, now just confirm this actually. If we look at the console, dot A to Ds in this case returns this array. So because this is a regular Ruby array, there's a Ruby method called each with index, which will be useful here, and that will automatically pass in an index counter as well into this block here. So what we can do here is we can say define A to D, and then this will be the index counter. And this will be the same, and then this looks like the base address here. So we can say A to D dot base address. We can just say to hex on that, just format it. It looks like there's some characters on the end of this, which I'll just leave. Okay, that's good, we'll verify that. And look at our diff here, so that looks perfect. I've got two A to Ds in our model, so I've got two lines and I've got our base addresses in there. So the last thing we need to do now is this, this section at the bottom here. So we'll save this off. And this looks like basically a combination of the two loops we have. We need to loop around each A to D instance. And then within each A to D we need to loop around the registers. So we'll just copy really what we've done already. So we'll take the A to D loop, and then we'll take the register loop. Just indent that nicely there. We can get rid of, all of these now. I do want to have a space between each of the A to D instances, so I'll put a line in there, and then I can just delete all this. Okay, so again we'll just go through this and substitute what we need. So let's make this whole thing a string again. In fact, let's think about this. Okay, so let's do this. So we'll say A to D, and that's going to be the index. Then this is going to be the register name. So we name the string the uppercase again. Now let's say we want to left justify that. So we'll say dot left justify maybe 20. Then we'll say we'll add on this additional string here, which is going to be again A to D index. The name, R, and then again we'll left justify that with an R20, and then we want the register description again on the end, so we'll just copy that from up here. Okay, let's have a look at that finally. And have a look at our diff here. So this looks good. We've got A to D0, all the registers all nicely aligned, and then we've got A to D1, again all nicely aligned, and that's us done. So let's have a quick look at the file itself. Okay, so here is our completed header file for our A to D block. We can see all the registers here. We've got a sort of register summary for A to D down here, and then another one down here. So that's that didn't take very long to do, and now we've got a header template which will work forevermore. So if we wanted to change that header to make it include every single IP, what I would do in that case is there's another API called .subblocks, or if you prefer .children, it's the same thing. This returns a hash of all the subblocks in the top level model, or any model actually, if we're talking to the top level model. So we can see here that it's got the two A to Ds in this case. So within the template we would just say something like .children, .each do, and that would be the name and the block. And then we just wrap that around the existing code, and then we'd say block.regs.each_do and so on. So I'll leave that as an exercise for you lot if you want to do that. But hopefully that gives you a good idea of how the compiler can be used in the real world. Within NXP we use that a lot for generating things like this, header files. We use it in design. Some design groups use it to compile RTL and to create sort of test bench configuration files, that kind of thing. In test engineering we use it a lot for compiling any custom tester code we have. So for example C++ code or Visual Basic code, we pre-compile that through Origen so that we can pick up all of the attributes from the model. So we've basically got a single source definition of that model, which then is referenced everywhere else, rather than duplicating all the definitions within the Visual Basic code or whatever. So hopefully they give you some idea. Feel free to ask questions on the website. We'd love to hear from you, and hopefully you have fun using Origen. Thanks a lot. Bye bye now.